several applications for that program end in 3 weeks.
I have one more comment. You were offered a possibility to visit the Einstein archives, and I want to be sure that everybody who wants to go already registered, because it is, I think we already passed the deadline, but just to be sure that there's nobody who missed this if he wanted to visit it.
So maybe you could tell them, those who go.
Well, they have to tell Anat.
When it will be.
It's tomorrow. Maybe it's 4, if I remember correctly, it's between 4 and 5. It's written in the program, between 4 and 5:30 and 5, I think. Maybe we'll shift it to 3:30, depending on how many you are. So it will either be from 4 to 5 or from 3:30 to 5. Okay, so you all got the message.
You might also tell them what was there and why it's.
So you're confirming now? So please send to Anat the message.
Do they know what it is and why it's so special?
Why don't you explain?
It really is special. You all know, you've heard about Albert. You can really see documents in his own writing. It's special. So those of you who care about physics beyond last year and next year, I strongly advise you to go. It's at 4.
It says 4, but we could make it 3:30 because of the coffee break. It depends how many there are, because there is a limit of the number of people which can come at a given moment.
As for those of you who are interested in physics of the next year, as David said, there will be this program a year from now. It's, I think, after maybe 15 years that at KITP we are having a program encompassing all aspects of string theory, and that literally means from string phenomenology, compactification, swampland, various approaches to string field theory, non-perturbative definitions of string theory, holography, quantum information, dualities, supersymmetric gauge theories and gauge string dualities, deriving some of them, and I'm sure I'm missing some more, celestial holography. It covers everything that I think string theorists have been working on. And the idea is that the string community is sometimes in danger of getting fragmented in everyone with their narrow focus. The idea is to bring together people of different persuasions and get them to talk with each other, get exposed to some of the exciting ideas that people are pursuing, ask new questions, form new collaborations, and that KITP is the ideal location for that. So we welcome young people. Of course, we can't promise because these programs tend to be oversubscribed, but please apply anyway, and we look forward to seeing many of you there. So let me continue with the theme with a brief recap. So what have we done so far? So I started with a claim about the generating function of correlators of the Gaussian matrix model or any general one Hermitian matrix model. You can look at these correlators, genus G, endpoint function, and I made the claim that away from any double scaling limit, there's a dual description of this in terms of a closed string. I spent a little time, though I didn't explain it. The claim was explain it fully, but the claim was that it's dual to these correlators are given by physical correlators in a model topologically twisted theory on the SL2R mod U1 coset at the special level of the SL2R at level 1. So this was a claim, but we actually could verify this claim by something I tried to explain to you through by using a certain identity between two different matrix models, and this identity, which followed by something which I was calling open-close string it's an open duality of two different open string pictures, both being dual to a single closed string, but mathematically just followed by some matrix manipulations, the Hubbard-Stratonovich trick, and so on. And that enabled one to map the generating function of these correlators to that of a different matrix model, which had already appeared in the literature in the context of the C equals to 1 string theory, which in turn had this description in terms of this topologically twisted SL2R level 1 mod U1 theory. So through a somewhat indirect chain of arguments, we gave evidence, strong evidence for this claim. But as I said in my first lecture, the idea is not so much, I mean, this is, I think, a new claim, a new statement of duality, but what is for me more interesting is to see structurally why this claim is true. And so today I will try to move a bit in that direction, and also this will also set the stage for the next stage of complexity beyond the matrix models, that is the ADS3 times S3 theory that I mentioned in the first lecture as the So first, I want to begin this lecture by telling you something about Gaussian correlators. Now, matrix models, I think probably many of you have seen. They have arisen in many incarnations in many areas of not only high energy physics, but theoretical physics. But there is one fact, one striking aspect of matrix model correlators like these. Let's say we take a Gaussian for simplicity. It won't matter. I mean, just complicate things to add potentials. But there's something, so you might think this is very simple and you know everything there is to know about it in principle, but there's one very interesting, striking interpretation of this which I think should be better known among physicists. It's known to some mathematical physicists, and it actually goes back to an observation of Itzigson and Di Francesco. So let me first, this is what I'll try to explain. So when we try to compute something like this, what do we say? We say it's sum over Wick contractions of, and here it's a Gaussian, so the weight is 1 essentially, there's no real weight. So it's essentially over 1, but over plane diagrams, Feynman diagrams of genus G. If I'm genus G with n vertices. So you draw, so this is, of course, your pragmatic approach to computing this. You just sit down, enumerate all the graphs, and just sum over them with a trivial weight, maybe some symmetry factors, and so on. But that's what you would do, right? But there's a way to write this in a more mathematical way, which is much more suggestive of the interpretation that I would like to make, which is, so this can be written as, and I'll explain this in a moment. So let me explain what I mean by this. So this is, of course, the weight and the genus associated with this. But now I've introduced alpha, beta, gamma are elements of conjugacy classes.
You're not summing over beta here?
No, so beta will be fixed. I'll explain what these are. So beta is a fixed thing. So conjugacy classes in the symmetric group Sk, that's a symmetric group of k elements, where k is just summation ki, the number of powers of the that appear over there. And so these are elements of this conjugacy classes, so there are permutations. And these permutations are associated with the vertices, edges, and faces of the Feynman graphs that you would have drawn. And let me explain that. So with the vertices, we associate this beta, which belongs to the conjugacy class of cycles of length k1 up to kn, the same set of k's. And you see that's an element of Sk because summation ki is k. Okay, so this captures the cyclic information at each vertex. And why is that? Because you see, so what is the underlying, what's the underlying reason here? What are we doing when we compute trace m to the ki? Each trace m to the ki is a string of m's with the indices permuted cyclically. So I1, I2, I2, I3, I3, I4, so on, and coming back. So that's a cycle of, it's a cyclic permutation of length ki, and there are n of them. So that's something that you would associate to each vertex. To each edge, you can also associate a permutation, and that is what I call alpha over here. So alpha belongs to the conjugacy class of just two cycles, transpositions. And there are k by 2 of them, because you see that's also of length k. K, by the way, has to be even for this thing to not vanish. Otherwise, you can't big contract in a Gaussian correlator. So k is, so this belongs to this, and this I claim is associated with edges in the sense that it captures all the possible Wick contractions. Because what is a Wick contraction? The basic Wick contraction here is something like mi1, i2, mj1, j2. You sort of Wick contract like this. So it's a, you don't need to contract all of them. I mean, you can have many of them. So let's say you're contracting some pair of indices. And these could be in different traces. These could be when we could have some contraction here. In fact, in general, I'll take normal order traces. So I'm not self-contracting. I'll contract only across. But anyway, that's a technicality. But you're basically identifying different indices across the different traces. So everything, that's a two-cycle permutation that is making this identification, just like in the vertices we had a cyclic permutation where you had I1, I2, I2, I3, and so on. Now, there you made a cyclic identification, but here it's just a two-cycle identification between these half edges. And then finally, there is gamma, which is associated with the faces. And so faces, I associate gamma, but gamma is actually just equal to whatever, alpha, beta inverse, alpha inverse. So gamma is also fixed in some sense. So gamma is beta inverse, alpha inverse, which is, it captures the cyclic arrangement of color indices around each face. Because once I make all these big contractions, I get naturally some color indices going around each face, which is, again, some cyclic sort of identification. But that's fixed. Once I give you the weak contractions, then the rest of it is fixed. So that's why, in some sense, I have this delta function. This is a delta function which tells you that alpha times beta times gamma is 1. So it's really a sum over only big contractions, like we just had in this informal presentation. So this is a more formal presentation of what we informally kind of talk. And you can convince yourself. It's just a matter of messing around with the indices and convincing yourself that this is true, even if maybe all the details are not clear. But you can plausibly believe that this is one way to organize this sum. And so this is a very...
And maybe one or two graphs that would help.
Yeah, I could do it in a tutorial, maybe I could, because it might take a little while with all the indices, yeah, so...
and the claim is that captures all combinatorics.
All because it's basically, see, this is a bit of a fake, the way I've written it, because there's a delta function, so it's really a sum over alpha. And alpha is basically this big contractions. So and that captures all the combinatorics.
G alpha beta gamma?
Yes, I will just come to that. The genus, I will come to that in a moment. So at the moment you just think of this as a genus associated with the Feynman graph. But there's a natural interpretation of that in terms of alpha, beta, and gamma as well, which I will come to in a moment. But yeah.
But it's not, I mean, it's not G.
It's the same G. It's the same G, but I'm writing it here G as a function of alpha, beta, and gamma just to show, just to kind of make it explicit that the G is, in a sense, fixed by alpha, beta, and gamma, or basically alpha, but just to write it in a more symmetric way, yeah.
Don't we have a dependence on the parameter T2, which appears in the construction?
You could put that, I put it equal to 1, but there would be T2 to the k by 2, something like that, because each contraction comes with the power of T2. But that's an overall factor. Okay, so why is this a good way to represent this contraction? By the way, this is true, I mean, this captures the combinatorics of the Gaussian correlator, but it underlies the combinatorics of all large N free correlation, because it's the same principle of so basically you can therefore phrase it as that this correlator is counting all permutations alpha, beta, gamma subject to these conditions. So it's basically a count of permutations. Now, a count of permutations, as understood by Riemann long ago, a permutation can be associated to a covering map or a branched covering. And let me just very quickly explain that. So for mathematicians, counting permutations is the same as sort of counting holomorphic coverings. So why is that? So that's because permutations can be associated with branching structure. All right, so that will help to answer Shmuel's question about what is this G, and so on. So I'm coming to that. So what do I mean by this? So let me draw some things with a colored. Okay, so let me explain this picture a bit. So this is a picture of a branched covering of a Riemann surface over another Riemann surface. I've called this sigma t target. This is what we will identify with the Riemann surface associated with this genus, which will be the world sheet. So that's why I've called it sigma ws. And it's a branched cover. So in general, there's a multiple cover. The degree of the covering is the number of pre-images at a generic point. So in this case, there's 7 pre-images. So it's a degree 7 covering in this case. It has a branch point at 1, which has a branching 2 here and a branching 2 here. So that that corresponds to the fact that now I can associate a permutation to this branch point, because what happens when I go around the branch point is that I permute the sheets of the cover, and I go from this sheet to that sheet. So this is a permutation of order 2. This is another permutation of order 2. So this would be an example of 2 of these alphas, whereas here above 0 I have a permutation of order 3, because it's a 3-sheeted covering. The 3 branch point of order 3, like z cubed locally, the branch. So branching z to the k is of branching k because of the k-fold cover. So this is associated with the cycle. Let's say in this case, I mean, there's not 2 square, 1 cubed, because here there's a cycle of length 3. This is associated with a permutation 3 and 1, 4. So they're all degree. This is a degree 7 cover. So it's a permutation of length 7. Don't necessarily identify this with this. Here, k has to be even and so on. But just the general identification of permutation structure with branched points of a branch covering of a Riemann surface by another Riemann surface. There's a question.
when you're saying Z cube, is it Z cube or Z to the power 1 by 3? Like how you are.
The covering map is Z cubed.
Oh, I see.
So the inverse, that's why it will have three images. So this is the target space, and this is a, yeah. The branching over one, yeah. So, so if you wish, this whole thing is a Riemann surface. There's a point here which is, say, Z1. There's a point here which is Z2. Then there's Z3, Z4, Z5. Locally, near Z1, it looks like something like 1 plus Z1 square. Near Z2, again, it looks like 1 plus Z2 square, because the covering map is mapped to 1, the point 1, that's why there's 1, but it's of order 2. Whereas near Z3 and Z4, it's regular. It's 1 plus something Z3 or Z4 or Z5. So that's what. So this is the local, this tells you what the local structure is of the covering map near each of these points. Yeah.
Is the permutation or the mapping maintains like the structure of the graph, like which edges are connecting to which?
Exactly. That's what this is designed to do. This is designed to capture that, because when you do the Wick contractions, you're essentially what you are doing is you do the edge Wick contractions. That is determined by you've already specified a cycle structure when you specify your external vertices. So that's beta, that's sort of fixed for you. Then each Wick contraction gives you one way of identifying the color indices and forming a color loop, which is what gamma is gamma. So you have these alpha, beta, you sum over alpha, so in the process you sum over all possible gammas, but the gammas are not independent, they're related to beta and alpha in this way. Yeah.
And near the point 0 is Z cube?
It would be Z cubed. It would be whatever, this is some Z6 or something, yeah. It would be Z6 cubed. So if I call this X and this as, well, I normally do it the other way. So the world sheets of Z and this is X, so X of Z is like Z, near Z6 going to 0. But near X going to 0, which is.
And this 1 to the power 4 means.
I should have, sorry, I wrote it in a wrong way. It should be Z minus Z6, the whole cube. This should have been Z minus Z1, sorry. This is how it looks in the vicinity of Z equal to Z2 and so on. So Z minus Z2 the whole square, Z minus Z1 the whole square, and here it's just 1 plus Z minus Z3. But here it's just Z minus Z6 the whole square, whole cubed. Okay, so this is, in a sense, as I said, it goes back to Riemann, but somehow as physicists we don't think of it this way very much, but I think it's a very useful and powerful way to think of it as, and this will recur in the ADS3 case as well. I'm saying now for the Gaussian, but this whole machinery and the underlying thing will crop up again in ADS3, and I believe in ADS5 also, though there we have not completely fleshed this out. But, okay, so let me answer Shmuel's question.
It's associated with a collection of permutations.
Yes, a branch gum.
Structure. And that associated with these correlation functions, you say?
Yeah.
How does that work?
So for each Feynman diagram, there will be a covering map. So this, what let me say the outcome. So each Feynman diagram, which we think of as coming from a particular big contraction, or in this language, a particular alpha. So this corresponds to, so a Feynman diagram corresponds to a permutation alpha, which corresponds to a covering map, if you wish, gamma alpha of Z, which will have its thing, and we'll finally say that this corresponds to a world sheet, a point on the world sheet of the string theory, a world sheet which belongs to the moduli space of the genus G. And so it'll be, so it's a refined mapping that each Feynman diagram will correspond to a permutation, which will correspond to a covering map, which will correspond to a point on the moduli space. And then you, summing over all permutation. Sorry? I'll draw one little later in this thing, which maybe, but let me still build up some more machinery, some more points in this. Yeah. Beta is just a cycle structure which is in K1. In the covering map, yeah. So so okay. Here I was just associating to any permutation, any set of permutations, a covering map. So a permutation corresponds to a branch point. So beta could be, say, one of these or one of these. Alpha could be the other one. So think of this as maybe alpha, this as beta, though it's not correct in detail, but
the alphas are only two.
Two. So yeah, but if I had drawn maybe one more, I could have drawn, say, one more like that. Then this could, well, no, this would need to have, all of them would have to be branching of order 2 in this. So so this diagram doesn't correspond to any particular this thing, but you can draw one in which above 1, the only things that are there are branch points of order 2.
What is the genus of this?
Yes, I will. That's what I'm just going to explain. It's given by the Riemann-Hurwitz formula. But I will, let me explain that. So the branching number is associated to any branch point. So B is, supposing I have a permutation K1 to Kn. So as I said, each permutation corresponds to a branch point. So what is and this means that locally there's a branching of order K1, K2, K3, Kn. So the branching number is defined as Ki minus 1, because when it's K1 equals to 1 is trivial branching. There's no branching really, so that doesn't contribute to the branching number, so that's why the minus 1. So the simplest is the branching of order 2, which gives you a 1. So this is the definition of branching number. So now let's compute the branching numbers associated with this alpha, beta, and gamma. So the vertices B beta, that's essentially this, because I use the same notation. So what is this? This is K minus N, because summation Ki is by definition K, and this gives you N. So it's K minus N. That's the branching associated with alpha, with beta. With alpha, it's very simple, because you get branching of order 2, and there are K by 2 of them. So each one gives you just 1. So this is just K by 2. And what is gamma? Now gamma, I told you implicitly what it is, but you can think in the language of Feynman diagrams that it's associated with the faces, as I said. So there's one per face. one cycle structure per phase. So if I have a phase of order 5, this is a cycle of order 5 associated with the phase of that Feynman diagram. So it's basically you're identifying this. So these were some vertices of the Feynman diagram, things going there. So you're identifying this color index with this color index, with this cyclically it goes around. So it's cycle of so you have as many cycles as there are phases, and the total number summation ki, by the way, that you know is always k, because that's the degree of the full permutation. So this is k minus f, where f is the number of phases, because summation ki is this, and the number of cycles that are there, you have one cycle associated with each phase, so it's k minus f. Okay, so the total branching number is defined as, is just the sum of these three, because here there's only 3 branchings. There are only 3 permutations. And so this cover, whatever it is, has only 3 permutations which are associated with the vertices, edges, and faces. And this is, if you just add this all up, you get 5k by 2 minus n minus f. Okay. Now there is the Riemann-Hurwitz relation, which you can also prove very easily. You can see in textbooks of Riemann surfaces. It basically tells you that, okay, let me write it down. Where if I have a covering of a genus G to a genus capital G surface, and this is a degree D. So remember, degree is just the number of pre-images, which is also the length of the permutation. So when I have, so this is the degree, because that's the number, total number of pre-images. So if I have, so in our case, let's apply this. So in our, this is the general formula, Riemann-Hurwitz formula. In our case, D is equal to K. We don't know what this surface is, but we know we have 2 minus 2G plus 5K by 2 minus N minus F. So this is, B is the branching number. Okay, so that's the Riemann-Hurwitz relation. But so you actually see that the way I have written, this is actually so V minus E plus F is so V minus E plus F of this Feynman graph. V, the number of vertices is n. The number of edges is k by 2, and F is the number of faces. So this is 2 minus 2G. So
Capital G.
yeah, capital G in gen is the genus of the target space. Capital G is of this one. So it's a covering. So this is general, and for us, G will be actually turn out to be 0, as we'll just see in a moment. So so V minus E plus F is this. So if you just put this in over here, you just get this is equal to 2K. So this implies G is 0, because you see the right hand side is 2k, and this is already 2k. So this tells you that these covering maps are covering maps from some genus G surface, where the genus is given by what you would naively associate with the Feynman diagram. So that's the V minus E plus F of the Feynman diagram, to a target space of genus 0. Actually, you could have seen that this target space must be of genus 0 because of this relation, that gamma is beta, alpha, beta, gamma is 1. That's the statement that if you go around these 3 points, the monodromy is trivial.
This is essentially the large N planar.
Yeah, this is in the target space. Here it's genus G, but the statement is that the monodromy in the target space is trivial. So this is actually, so these are covering maps from genus G to genus 0. So
Why would you have expected genus 0?
Because, okay, to just give away a punchline, the genus 0 is basically that cigar, or as I learned yesterday from Eliezer, cucumber geometry. So of the SL2R mod U1 theory. So it'll be maps from the world sheet to this target space, which is of genus 0. But yeah, so that's why it's natural from the other point of view. But at the moment, it just follows from the mathematics of this permutation. So the bottom line.
This Riemann in general, relation between permutations and covering spaces, in general, would give you maps to arbitrary genus
Yeah.
covering spaces.
In principle, you could get to arbitrary space, this thing,
Right.
yes.
And the Gaussian Feynman graphs, large N, gives you just genus surface.
Exactly.
Genus 0 target space.
Genus 0 target space.
Is there anything in physics or metrics models that would map you to higher genus target spaces?
I think so. I think, for instance, the dual to 2D Yang-Mills that you had
Yes.
will be something where the target space. So you could consider, and I think in ADS3, for instance, we'll also see the target space as a sphere, but that case, that is because the boundary of ADS3, Euclidean ADS3, is a sphere, S2. So there also we'll see its target space is a sphere, but you could in principle consider thermal ADS in which the boundary will be a torus, and you would have holomorphic maps to a torus. So I think and in ADS3 you could in fact consider also higher genus boundaries. Yes?
Can you please repeat what affected G is and what it is corresponding to?
So this is the Riemann-Hurwitz relation is a general relation for branched coverings, holomorphic branch coverings from a genus G a Riemann surface to a genus capital G surface. And that's given by this, where D is the degree of the covering, the number of pre-images, capital G is this, small g is this, and B is the total branching number. So that's the relation. And it's not difficult to prove. You can, as I said, check it. In our particular case, we had B I computed for you from these 3 branching points, and B minus E plus F is this, which is the genus of the Feynman diagram, and that when you put it in, you find that the right-hand side is 2k, so you learn from this that capital G is 0. So what you learn, so the bottom line to summarize is that these Gaussian correlators are counting inequivalent holomorphic covering maps from sigma g to a sphere branched over 3 points, over exactly 3 points, which is important. And you can take those to be 0, 1, infinity without loss of generality. So you're basically considering these. So you're counting holomorphic maps with some specified data, for instance, that beta is k1 to k1 to kn, so they're implies the degree is equal to k, which is summation ki. So you're counting basically holomorphic maps of this degree with this given branching structure at, say, 0. So beta, let's say, is this, and this is, say, alpha, this is, say, gamma.
Sorry, what is a cigar?
No cigar, I mean, at the moment.
No, you mentioned before.
I was just anticipating when David's question, he was asking why is the target space P1? So it turns out that it's because it's sort of like a compactified cigar. The other end will be a cucumber-like end, and that's, I think, special to the topologically twisted cigar.
I don't think that Eliezer meant that cucumber. I think he meant to call the cigar the cucumber.
Anyway, I like the term because it fits what how I think about it. So, so any case, now these such holomorphic maps branched over exactly 3 points have a special name in the mathematics literature. They're called belly maps, and they form the basis of a large mathematical literature. You might think, oh, why special? What is special about these? These are some 3 points, one can give many lectures on them, but it's of great arithmetical significance and so on, because one reason which will be important to us is not every point on MGN admits belly maps. So covering maps are very rigid objects. You can't, if I define an arbitrary Riemann surface for you and ask, will there be a covering, arbitrary point in the moduli space of Riemann surfaces, and ask, can I find a covering map to genus 0 exactly 3 branch points? And the answer is no. There are obstructions. In fact, there are only discretely many points which admit these covering maps. And these are called arithmetic Riemann surfaces. So that's part of the reason why mathematicians are interested in them, because they are arithmetic in the sense that you can find a presentation of the Riemann surface in which all the coefficients are algebraic numbers as opposed to a generic complex number. And so these are very special for mathematicians. And I think Grothendieck in the last 10 years of his mathematical life, I think, spent time trying to understand this, this Belly theorem. There's a theorem of Belly here. He called one of the greatest revelations for him, because it helps in the classification of what mathematicians like to think of as the absolute Galois group. But anyway, it's related to a lot of number theory and so on.
What's the great theorem say?
The Belly theorem?
Yeah.
Well, so that is the if and only statement that if the Riemann surface admits such a Belly map, only if it is arithmetic. So this is Belly's theorem, that an arithmetic surface is one that can be defined over algebraic numbers. So it's a special set of points on the family of Riemann surfaces. So there's alternate ways to characterize them, which I can maybe talk about later, but there was a question.
Suppose when you say that alpha, beta, gamma are in the conjugacy classes of the symmetry group, why do we consider only permutations but not also transpositions?
transpositions are included. I mean, 2 to the k by 2 is a set of only transpositions, Z2. Permutations of order 2 is basically transposition.
So, Rajesh, I mean, you got Riemann surfaces with only handles with no holes, right? No points.
Yeah, you can say the marked points, because I will talk about marked points where I'm inserting the vertex operators, but no holes. Okay, so this, as I said, I mean, I find this to be a very significant fact, and I think we now are beginning to see why it is very relevant in string theory. And as I will try to tell you, this pattern that I'm explaining here will recur in the ADS3 symmetric orbifold case. So I will start with the symmetric orbifold, and we'll see a very similar thing happening in that case. Except it won't be belly maps. There'll be more general coverings, but the Gaussian is associated with belly maps. Okay, so what I want to do is identify this with the world sheet. So as I said, I want to identify each such point which corresponds to, which admits such a covering map with a point on the world sheet. But then that would suggest that the dual string theory must have the
You mean by a point on the moduli space?
Point on the moduli space. So a particular point, namely these arithmetic points. So that would suggest that your dual string theory must be quite unusual, because it must get a set of contributions which are localized, delta function localized at certain points in the moduli space. This is not something you normally come across. It sounds outlandish at first sight, and I think this is the reason why people, when they studied the the matrix model, went towards the double scaling limit, because then you cover the whole moduli space. By the way, these arithmetic surfaces are dense in the moduli space, because you can, as you make these operators bigger and bigger, you can sort of basically cover the whole of moduli space. But just like the rational points are dense in the real time, even though they're not.
Not the rational, the algebraic.
Well, these are algebraic Riemann surfaces, yes. So the exact density is, I think, something actually mathematicians are studying. It's not completely answered yet, but they are dense, at least that is known. How dense, I think, is a different question.
There's always an infinite number of such points.
Infinite number of such points. Of course, for any fixed cycle structure, there'll be only a finitely many. So, but it will grow with. So that's why if I have operators k1 to kn, for k1 is 2, all the k's are 2, there'll be maybe 5 points on the moduli space that will contribute. But if k's are 10,000, there'll be probably like some exponent, it grows some power of k to some k to the n minus 3 or something like that, it grows. So so the number of points will be very large. So in that sense, even the Gaussian can see, if provided you probe it with larger and larger operators, you can see more and more of the moduli space. The small operators see only a few points, but the large operators, the BMN-like operators, they see more of the moduli space.
The Gaussian polynomial in K?
I think so, if I'm not, k to the 2n minus 6, if I'm not mistaken, something. The number of covering maps, yeah.
And so in some limit, if one adds these things, it actually expands as a factorial function.
Right. In the core, no, but for the given genus, it's polynomial.
Yeah.
Yeah. The total number is factorial, but there's a finite radius of convergence. So, okay, so now let me try to say, so this was sort of outlandish, why we have, might have only these discretely many points. There are precedents in topological string theory on T2 and so on, which people have studied, where this is known to happen, but I think a big boost was when we studied the tensionless limit of ADS 3 times S3 times T4, where, as I will try to sketch a bit, this happens again. But I think for the same reason, it happens here as well. And in fact, the localization is precisely to these points. I mean, these are not any old set of points on the moduli space. You have to localize to these arithmetic Riemann surfaces. So a very stringent check is if your worldsheet theory, worldsheet correlators that you compute, have this delta function support precisely on these points which admit these covering maps. And this was one of the things which we saw, that the SL2R level 1 theory correlators of special operators in that theory, the ground state operators, have this property. So let me say a little bit about that. Yeah.
Is it not true that the moduli space of Riemann surfaces is identical to the moduli space of flat gauge connections?
Of SL2R, yeah, there is a way of thinking about SO2, 1, yeah. Yeah, I don't know in that language what these points correspond to, what special connections these correspond to. Yeah, that's an interesting question. I don't know the answer. So, okay, so okay, so so I'll just very briefly maybe say this in the interests of time, or okay, maybe I'll come back to this later when I talk about the ADS 3 times S3. And so at this stage, let me just say that the dual string theory needs to localize onto these special points on MGN. If this picture of how the Feynman diagrams correspond to worldsheets is correct, then whatever your proposal is for the dual string theory, it should have this property. At least there should be a presentation of the dual string theory which has this property. Because there might be other presentations where you don't see localization, because the integrand on moduli space is a bit of an ambiguous object because it's defined only up to total derivatives on moduli space. So you can sort of mask that property, but if you can find a presentation of the correlators on moduli space which has this property, then that tells you that that's at least a way in which, or it's a gauge in which you can see this happening. Okay, so yeah. So I'll just tell you two things because I said a couple of things about the dual string theory. So without, and this, I must say, some of this is something we are still actively trying to flesh out, but you'll see that in what I said in the previous lectures, there are some ingredients which match exactly with this property. So I'm claiming that the SL2R has this property. Okay, so there are some non-trivial checks which I think I can tell you without any detailed explanations. So some non-trivial consistency checks that this passes. So the first is the dual, so the claim is, so there must be something in the dual string theory. This correlator, you want to have such a property. Now, these, I mentioned last time a little, that they correspond to some very special representations of the SL2R level 1 theory, which can be thought of as being in the kth spectrally fluid sector K, which K is the same as this momentum K. Remember, this is the thing that is dual to trace m to the K1. The original Gaussian correlator we are considering here. So these are dual to these special representations. Each of these representations of SL2R in the kth spectrally fluid sector creates a branching of order K1. That's something you can see from the definition of the spectral flow itself. And this is something in the ADS3 case as well was very important.
I try to recall, it's a topological string theory, right?
Yeah.
So if I remember correctly, these are correlators.
Are holomorphic. Holomorphic maps.
Parallel ring, and this is
the correlator, yeah. So these are the ground states of the spectrally fluid sector, which correspond to that. And in fact, it is because it's the A model that it localizes on holomorphic maps, which is what we have over here. So, and these holomorphic maps, these representations create a branching of order K1, where they are inserted exactly like this. So this would be in the 2 spectrally fluid representation. This would be in the 3 spectrally fluid representation. And so you have so the external operators create exactly the same kind of branching of K1 to Kn. So this gives you automatically the cycle beta. So this gives you the cycle beta, and so they are all sort of mapped to, if you wish, infinity or the boundary of the cigar. This is what I was saying, that you kind of pinch off the cigar on the other end. So, or like this cucumber type of thing. But so you have the cycle beta associated to this. So now this is your target space. What I was calling sigma t. And there's a beta associated with that. And remember, I had this background of momentum 2 turned on, tachyon momentum 2, which was very special and might have seemed very odd. But you see that that background momentum 2 is very important, because that, I mean, if I just consider tachyons, these were mapped to some kind of tachyon or this mode scattering amplitudes. Normally, if I don't turn on any background, this would be 0 by momentum conservation. You would, because these are all momenta, negative momenta K1 to Kn, you would need equal and opposite positive momentum to cancel it. So if I didn't have any background, this would be trivially 0. So you need a background, and in our case, the background has positive momentum 2. These were negative momentum minus K1 minus Kn. And how much? So you need to pull down from the exponent. When I'm turning on this background with momentum 2, you need to pull down. And how many of them you need to pull down? Summation Ki by 2, which is K by 2 of these momentum 2 operators. So you see this, the number, so when you really evaluate this correlator, what you're really evaluating is this together with K by 2 of momentum 2 operators. And that corresponds to the cycle alpha, which I was talking over here, because that's precisely 2 to the k by 2. And so you see the same 2, which appears in the big contraction that over there, arises here very naturally because you're turning on that background 2 of exactly that same momentum. And you need exactly, momentum conservation tells you that you need exactly as many of them to balance this thing. And finally,
Why do they all sit at the same point on the target space?
Yeah, so it's a good question. This is something we are trying to understand better, but very naively, the point is that the theory is topological. So effectively, they all sit at the same point because the movement in that direction is like a BRST trivial this thing. But I'd like to flesh that out better. That's why I said this is a sketch at this stage and this is in work to appear with Edward in future papers. But I think that's something we would want to this thing better. And finally, the third point, which is that if I now were to consider just that scattering amplitude of all of them, the positive momenta and the negative momenta, the way it was conventionally done in this equals to 1 string theory at least, is that there's sort of this Liouville wall of which they scatter, and that's what creates the S matrix for the scattering. And that's what we would like to identify with gamma, which is sort of the tip of the cigar, where the rest of the interactions is. So gamma would be the tip of the cigar, this cycle. So that's at least the sketch for how the dual string theory would have this precisely this alpha, beta, gamma, these 3 localization.
So you said that it's a topological string theory. In what sense? I mean, will this correlation function be independent
of the Z1 to Z? Exactly. That's one way in which. That's why it doesn't really matter. They just they'll be all mapped to the same branch point at infinity. The positions won't matter. That's what exactly. So anyway, that's. So that's, I wanted to introduce primarily this machinery here because we'll see that now I'll switch to the ADS3 case or more precisely the symmetric orbifold CFT, the field theory side, and try to tell you why very similar structures appear there as well. Okay, so so when I say the same structure, I mean this sort of this thing where, so here we'll actually see that in the symmetric orbifold, the logic will be slightly reversed. We'll start with permutations, because that's what the symmetric orbifold starts with. We'll be able to associate a Feynman diagram with each of these permutations. Actually, this was associated long ago by Bachman, Rastelli, and Razamat. There's a natural association between permutations and this. So this part, this arrow is sort of known for that case. But we'll see that this is related to, again, a covering map. And that covering map is related to a specific point on the worldsheet. And those points on the worldsheet are precisely what the dual string theory formulation in terms of a Weismann-Witten model gives you. So that will be the logic.
Not point on the world sheet.
A point on the moduli space, sorry. A world sheet, a given world sheet, which is a point on the moduli space. So we'll get, again, discretely many points, which in some limit will go over to the same arithmetic points, which I don't know whether I'll have time to describe that limit, which is also interesting and brings in another whole set of interesting maths, but let me at least say some aspects of this thing. So one of the things that has become more clear in the last few years is that the so-called free symmetric orbifold, namely you consider n copies of a T4 CFT and you orbifold it by the symmetric group that permutes these n copies. This is the free theory, so it's just a free CFT modulo this orbifold. So it's somewhat like the analog of free Yang-Mills theory, which is also free up to a Gauss law constraint. So here also it's free up to this orbifold action. So this is dual to some tensionless limit of AdS3 times S3 times T4, which is specifically k equals to 1 unit of NS flux. So, but let's start from, like we did in the matrix model, let's start from the field theory, and then we'll talk about the world sheet later. So the field theory, so the states in the CFT states or operators are classified by their twist under the orbifold action, which in this case is a symmetric group again, but now a symmetric group. So here this is in the large n limit. So this is also the symmetric group like we had earlier, but so there is, of course, there's the untwisted sector, which is Sn invariant, which will not play much of a role, but the twisted sectors are classified by, again, by conjugacy classes in Sn. So that's the general statement. If you look up any CFT book about orbifolds, that's what you see. So this conjugacy classes are basically the same kind of cycle classes. But what we will be interested in are sort of single particle states. What correspond to single particle states. So these are what in free Yang-Mills theory, or in Yang-Mills theory would have been single trace operators, but here they are what are called single cycle operators. What that means is that the conjugacy class here is something which is some k, and then the rest are all singlets. Okay, so there's one cycle of length k, and the rest are trivial. So that's the conjugacy class, you can say. So you could in general have had conjugacy classes with many non-trivial cycles, but those correspond to multi-particle states in the large n limit. But these are the single particle states, which we'll consider. So I'll call this a k-cycle twisted sector, or a k-cycle, because it's, so the kind of correlators, the analog of the trace m to the ki that I was considering there are now the ones that I'll mostly focus on. There are a larger set of correlators, But I'll focus on these correlators of the orbifold CFT, where these are the twisted sector ground states in the so each twisted sector has a ground state and many excited states. I'll focus on the ground state, so that's the notation. Sigma of Ki is the ground state operator in the cycle of length Ki. And I can consider a general correlator, K1's, it's like considering trace M to the K1, trace M to the Kn. Okay, so the other new thing from the matrix model, so you can again consider the genus G contribution, etc. But the new thing is that this this is the point of insertion, which will be on the boundary of ADS. So this CFT, the two-dimensional CFT we'll take it to be on S2, which is the boundary of Euclidean ADS3. So this is living on the S2, like a generic conformal field theory. So how do you compute such a correlator? It's a question in CFT. Just like I told you how to compute this matrix model thing over here, we say it's some sum over big contractions, etc. What's the analogous statement for computing something like this? So let's make that statement. This was actually done in a very clever way in a paper of Lunin and Mathur more than, I don't know, maybe 15 years. And it uses something that you have probably seen in some of the other lectures, especially of Ahmed or Netta. Netta probably hasn't come to it, which is a replica trick, which you use for these orbifolds. So the idea is of Lunin and Mathur. So we want to compute so the idea is go to a covering space. So what do we mean by that? So it's a picture very similar to the one I drew there. So maybe I can try to recycle that picture. Yeah, let's see. Let me draw it again. That picture is too cluttered now. Sorry. Not this, right? This one. So this will be. This will be a covering space, which will be again some Riemann surface, which I'll specify. And then there'll be a, so there will be a, this is my original X space, which is the S2, which is my boundary of ADS3, as I said. So this is the target space. And I have points which so I have inserted operators at say x1, x2, there could be many of them, x1 to xn. And so what I do is I go to a covering space in which I look for a covering space and a covering map, which has the same branching structure. The branching structure z to the, so here it would be branching of order 2, here I could have, maybe I should draw one, branching 3. So this is if I had sigma 2 of x1, sigma 3 of x2, and so on. So this is in, this is the label over here. There's a branching of order 2, branching of order 3. So I go to a covering space which has branchings of the appropriate order around each of these, at each of these points. So what does that mean? That means that I want to find a covering map x, which is some gamma of z. So from the z space, so this is the x space and this is the z space, which we'll eventually identify with the worldsheet once again, the z space to the x space, such that this gamma of z has the property that x equal to gamma of z is such that near z goes to some zi, it behaves as xi plus some constant it has a branching of, so this is how this covering map must look in the vicinity of each of these. So I'm looking for a covering map from a Riemann surface to this S2 such that near each of these points Zi, at Z equal to Zi, Z equal to Zi is mapped to Xi. So this is say Z1, this is Z2, and it has branching of order K, or Ki at each of these points. Is this clear? This is a mathematically very well defined question. If I ask, write down for me covering map which has these properties such that near for I equals to 1 to n, which has this behavior. This is a rigid problem, meaning that if I specify the xi's, I can find discretely many solutions. The simplest way to see is if you take the covering space to be, there'll be a constraint on the genus of the covering space, but let's say we have a covering space of genus 0. What are all the covering maps from genus 0 to genus 0? They are essentially rational functions. So you get some degree, so this is of degree n. A degree n cover, or maybe since I was using D, I should use D. So a degree D covering map has this form on a sphere. So it's a rational function of degree d, I mean a polynomial of degree d by another polynomial of degree d. And if you put in these conditions, you can show that the number of equations, because it's a polynomial, it has only d plus 1 coefficients here and d plus 1 coefficients there. So you can look at the number of equations that you need, because you see there's a vanishing. You know it has to vanish, all the terms between 0 and ki minus 1 have to vanish. Or in other words, the successive derivatives have to vanish. So you're getting many vanishing conditions. When I say this is equal to 0, that implies a lot of vanishing conditions for this. In fact, a useful way to say is that del gamma of z near z goes to zi behaves like z minus zi to the ki minus 1 times some prefactor. So it's telling you that del gamma must vanish up to order ki minus 1. And that gives you multiple conditions. So this is a rigid problem, and I can explain to anyone who's interested.
So, just right now, you talk about generic symmetric orbifold.
Generic symmetric orbifold.
Generic ABS3 is just
yeah.
some.
Yeah, so this is just a way of computing in the generic symmetric orbifold. Lunin and Mathur's prescription is very general. So what they say is that, okay, so why is this useful? So I defined the mathematical this thing. I'll just take 2 minutes. The chair is not here, so and I started 5 minutes later. So,
the chair is here.
The chair is there, but the capital chair is not. Why is this useful? Why did Lunin and Mathur use this trick? Because as I said, it's like the replica trick. What do you do in the replica trick when you have some, this means that there's some twist. This is a twisted sector of order 2. When you lift to the covering space, it's a single valued field on the covering space. So this lifts to an operator which has, in the case of the ground state, is just the identity operator on this space. Because there's, if I put an excitation, of course I'll have some excited operator here, but if it's the ground state, then it's just inserting the identity operator on this branch point. So evaluating this correlator, so you can, instead of evaluating this correlator in the X space, you use this holomorphic map to evaluate it on the covering space. You can just pull it back because it's a conformal mapping. So I know this, if I know this mapping, then it's a CFD. I know how it is in the X space. I can translate it to what it is in the Z space. In the Z space, it is just, in this case, just identity, identity, identity. So it doesn't matter. So basically, it's the partition function, because it's all identity. It's just the partition function, but now on this Riemann surface, which is defined by this covering map, gamma. So you might think, well, that's sort of trivial. It's not really trivial because when I have this, so there's a pullback here, right, by gamma of z, by this non-trivial covering map, which I would solve for some equations and find. So you know that in a conformal field theory, if I make a conformal transformation, I get a conformal anomaly piece, which is proportional to the Liouville action. So this is really e to the minus some SL of the conformal scale factor, which this is the sort of the Liouville action, which with the conformal scale factor, which is just del gamma squared, because x is this thing, so the del x is del gamma dz, or dx I should say, is del gamma dz, so del, and dx bar will be similarly. So the metric dx, so if I start with something at the flat metric dx bar, in the z space I get something which is mod of del gamma square. So I have a conformal factor. I have a pullback which has a conformal factor which is this phi, or rather this is, I think, log of phi. Yeah, of the e to the phi is this. So I have a conformal or a Weil factor which is mod del gamma square. So so you normally write, so no, sorry, it's log of del gamma square. Phi is log of del gamma square, where, so e to the phi is mod del gamma square. And what is this? This is what this Liouville action here. It's what you saw as the Polchinski-Strominger action in the last lecture. It's basically, I'm using even almost the same notation. Which is it's coming from the same conformal anomaly. So so it's just this. So the point is that this correlator, which seemed like a very complicated object to evaluate, can be written as, okay, I should have been a little careful. There's a sum over all the covering maps, because there can be many, there are discretely many, but so there's a sum over all the covering maps gamma, and each is weighted by this factor of this Liouville, this thing. And so this carries, because this knows about gamma and gamma knows about the x's, so this carries all the space-time dependence. There are some prefactors here and everything, but this is basically the Lunin-Mathur method for calculating these correlators. It's independently a very powerful method for of any independent of any ADS-CFT. But now maybe I'll stop here, and next time I'll discuss why this is the same, or why this is sort of in the same direction, though you probably are beginning to see some ingredients.
Theory on the long string in ADS?
Yeah. Yeah, this is, in some sense, I mean, it's a single cycle of length k, so that's what this covering space is telling you. And in some sense, you can think of it as action for that long string, but it's not something I've thought very much about.